Welcome back to the second lecture about descriptive statistics. Remember that with descriptive statistics, all we are doing is using numbers to describe what is with a data set. And statistic means that we're dealing with a sample, not the population. Otherwise, we'd have to use descriptive parameters. In this lecture, I'm going to talk about two kinds of descriptive statistics that are really important, and you will find these in every quantitative study that you look at, and that's central tendency and variability. And then in the third lecture, I'm going to talk about relationships. So we'll go ahead and get started here. Let me grab my notes here in case I had planned anything important I was supposed to tell you. There we go. Okay, so I'm going to start out by talking about central tendency. When I'm talking about central tendency, the first story I want to tell with this data set is what is a typical score? What should we be expecting? And so we use three pieces or three functions. We use the mode, which means that's the most frequent score. We use the median, which means I ordered my data set across and then I drew a line in the middle, and half the scores are below that point and half are above. And then we use the mean, which is the arithmetical average. So the first thing I want to know is the mode. So if I take my histogram that I showed you before and I line up all the frequencies of how often somebody scored 16, how many people scored 18, how many 20, 22, 24, etc., you can see that the most frequent score that exists in this data set is 24. That's all there is to the mode. It's just simply the one that got scored the most. Now, median is a little different, although it's very often the same number, and that's what confuses people. Median set means that I slice off half of the scores that are below and the scores that are above the halfway point. So you can see that I have sliced off the 4 scores below and the 4 above, and the median score, the one smack in the middle, is 24. This is another way that you'll see it done, where half of the scores are above that score and half are below. Now, be really careful. You'll notice that 24 is the median because I've ranked them all. It doesn't mean that 24 is the middle score of all the scores that were scored. It means that it's the middle of the frequency when I lined up all those scores. And then the mean, you're pretty familiar with this one. What you do is you take the sum, and that symbol is sigma, which means the sum. So if I add up all these scores, I get 490. To find the mean, remember we represent that with an X. I divide 490 by 21 different scores, and my average score is 23.3. So that's the mean and the median and the mode. Now, mean is used a lot, and it's a very, very valuable measurement for us, but it also can cause some problems. It's used a lot, and we use it for some further statistical descriptions that we do, but there can also be some problems you need to be aware of. So I'm gonna pretend here that in my I go and visit a soup kitchen, and everybody who's at the soup kitchen, I'm gonna ask them what they make each week. And so you can see I've ranked these out, and the mean income per week is $100.09. The median is 100. Think back to what that means. And the mode is also 100, the most frequently. So that gives me a sense of what the group is like. Now, imagine that someone walks in who doesn't fit that pattern. This is what we call an outlier. So look down at the bottom. All of a sudden, there's been somebody walk in the soup kitchen who makes $400 every week. Suddenly, my median is still 100. It's still in the middle. The mode is still 100. But look how much the mean has changed because of one outlier. All of a sudden, the mean looks like it's $153.92. And that mean is suddenly more than anyone else. Only one person in that group makes at least that much each week. So you can see that's one of the problems with the mean. We have to be very conscious of our outlying scores and what they do to the mean. In this case, mean is not very useful in describing the group because the mean for the group is more than anybody makes except for one person. You can see the problems with it. So now I want you to take a minute and try it. You can pause or you can walk along through with me. Here are, I think there are 11, 3, 6, 9, 11 scores between 1 and 5. So we're going to look at the mean, the median, and the mode here. I have to rank them to be able to do this. Some people can just glance at it and that's great. But I put there were 3 people who scored 1s, there's 1, 2, and then there's 4 3s and 2 4s and a 5. So I list them out. That's just easier for me. Then I can slice them in half. So there are 5 scores under this middle point and there are 5 scores above this middle point. So there's my median. It's 3. Now, before we move on to the next slide, think what the mode would be. What's the most frequently occurring score? Well, there they are. 4 people scored 3. So that was by far the most common score. Now, before I move on to the next slide, quickly add them up and divide by 11 to get the mean. And there really aren't any outliers in this, so you can probably guess that it's going to be about the same as the median and the mode. And it is. It happens to be 2.73 if I divided correctly. So this distribution is what we would call pretty normal because the mean, the median, and the mode are roughly together. They're all about 3. That means that my distribution is what I would call normal. So let's talk about shapes of distributions. Shapes mean that we represent them with histograms or frequency polygons to show where the scores are clustered. And then when we look at where the scores are clustered, we can say whether they are skewed or whether, and we can address their variability, which is their kurtosis, what the kurtosis measures is how much of a curve there is. So I talked to you about a frequency polygon. Here's a frequency polygon that you've probably seen a million times in your life, not even exaggerating. This is what we call a normal curve or a normal distribution. And all it is a frequency polygon. They took all the scores and they lined them up and they counted how many people scored each of those scores and then connected them with a line. So right smack in the middle is the mean. And it's in a normal curve or normal distribution. Look at how high that point is. It's also going to be the median because half of the scores are above it and half are below it. And it's also going to be the mode because it's the tallest, so that was the most frequent scored, the most frequently scored point right there. The mean, the mode, and the median are all at about the same point in a normal distribution. Now, what's really nice about a normal distribution or a normal curve, or what we would expect with a large group of people, is that one standard deviation below and one standard deviation above, 68% of the people who took this test should roughly fall in that darker blue area. So that's where your most frequently occurring scores are going to be. And it should include the mean also, or the average, 68%. Now, if we go out a little further, 95% of the people who took this test should fall along that green line that I've drawn there. So you can see that out into what we call the tails, way out in the ends, there are fewer and fewer people who got those scores, either really, really low scores or really, really high scores. And those tails are important too, because there's the people who score out there, there are not as many of them. Most people tend to score towards the center. 2/3 of them right around the center usually. Now, what happens if it's not a normal distribution? That's what we call skewed. Remember when I talked about how the mean can be changed by the outliers? Skewed means that the mean was changed by some outliers. If the mean ends up really, really low, in other words, there were more people scored, there were some people who scored so low that it actually moved the mean from towards the middle way down low. That means it's negatively skewed. And this is confusing for people because your eye tends to go to the highest point on the chart. But skewed means, where's your mean? Something is wrong if it's negatively skewed. And negatively means lower. The mean or the tail is way down in the tail, and that means it's negatively skewed. Positively skewed means just the opposite. It means that there must have been some outliers or some people who scored so high that it actually took the mean and moved the mean over towards the right. And this mean is just, it's almost like it's misrepresenting what really, really happened, because all of a sudden our average is positively skewed. So look at where the tail is. That it means that if it's skewed, it means that the mean is way over there. You can also see data sets. Remember, these are frequencies. So in this case, the most commonly scored scores are way up there at the top. So the one on the left means that it's unimodal. It's just got one place where the frequency shows up. But look at the model on the right, which is bimodal, or you can have multimodal, where there are several places where all of a sudden scores jump. Not the scores jump, but the number of people getting that score jumps. Now, kurtosis is the other piece that we need to look at when we're looking at a curve. And here we're talking about the range of the scores. If I look at the normal distribution, which is the green one, this frequency polygon, my scores range from very low, but there aren't very many people got that, all the way, and then the most of the people scored in the mid-range, and then there were some who scored over in the higher than that, and there's a good range or distribution of the scores. So there's my normal frequency polygon, my normal curve, or my normal distribution. Now, all of these three graphs all have the same range. But look where the scores fell. So on the blue one, there's not very much variation in this. Very, very, very few people scored these low scores, and then all of a sudden, everyone is clustered together. the most frequently scored scores are in a very tight, what we call a tight range. And this is a really high kurtosis when it does this. And then it falls off, and all of a sudden there weren't very many people who scored those higher scores. And finally, there's one that's a very wide distribution, and it's almost flat. It looks like almost the same number of people scored every score all the way along. And that shows that there's a very wide range in the distribution and a very small kurtosis. It's very flat looking. You got to keep in mind that variability matters. Look at these two sets of scores. Both of these scores have a mean of 80. But on the left, with set A, the range went from 79 to 81. So the scores were very tightly clustered, really high kurtosis here. And that shows a different picture of what happened than set B, where the mean is also 80, but look how spread out the scores were. And there was only one person scored each one of them, but it becomes very flat, very low kurtosis. And that tells me that I've got a huge variability in the scores. They went all the way from 50 to 110, whereas the one on the left, very tight. There's not much variability there to tease out. So when we're talking about variability, first of all, we look at the range from the minimum to the maximum. So in this one, I can have a minimum range and a maximum, and the range is the difference between the two of them. Look at the chart down below. I put a dot for each score here. On this one, the range is from 2 to 10. The range then is 10 minus 2, or the range is 8 in this set down at the bottom. So my example up above is not the same as the picture that I drew for you. You can see there. 6 is the mean. So we want to be able to tell our readers how far the scores are from the mean without them having to look at each and every score. So what we do is we calculate a standard deviation for them. And that means the distance we average the distance from the mean. So if my mean is 6, and this score here that was 8, I take the distance between those two, and it's 2. So I take the distance from 8 to 6. And I would take the distance from 9 to 6, and 10 to 6. And 5 to 6, and 4 to 6, and 3 to 6, and 2 to 6. And I would average all of those distances, and I would get my standard deviation. So, if you look at the green line, if I know that my standard deviation is 2, then my average distance of my scores from the mean is tight. You can picture it in your mind. But if I have a standard deviation of 4, which I've represented in purple there, then that's telling you that the scores are spread much wider, and the average distance from the mean to every score is much wider. So without knowing much about the scores, you can picture in your mind whether they're spread very widely or whether they have really high kurtosis and they're tighter and closer to where the mean score is. So let's go back to the normal curve or the normal distribution. In a normal curve, this ideal curve, 50% of the scores fall above the mean and 50% fall below it. That high point on the curve, the mean and the median and the mode, are usually pretty well at the same point. And overwhelmingly, most of our participants score near that mean. The further you get from the mean, fewer participants with that score. And each standard deviation represents a percentage of the scores. So remember that. So here on the left, I've got a standard deviation. Each of these lines represents my standard deviation, or my distance from the mean. And you can see that in a normal curve, they fall like that. So when you actually draw your frequency distribution polygon, it's not going to look like your normal curve, because your standard deviation is going to be unique for every set that you do. This is the ideal. Now I wanted to remind you that this, on the left, you've got a frequency distribution. On the right, it is not the same as what the kids actually scored on the test. It is counting the number of people who scored each of those scores. On the right, I've put in a graph of what their actual scores would look like. Same data set. So you can see that if each dot would represent a person and then their percentage correct. Let me repeat then. The normal curve is counting and representing the number of people who scored each score. It is not the same as graphing out the scores that the kids got. That would look like the one on the right. That leads us to being able to rank the kids, to line them up. I keep talking about kids, but it could be any kind of score that we're studying. But we could line them up from the lowest score through to the highest score. And this is where we get percentile ranks. Percentile ranks simply tell you the percent of scores that are at or below that score. So in this case, if I say that I want to know where 2/3 of the height scores are below. Where's the 2/3 point? So the 67th percentile. So I draw that blue line across and I've ranked all their heights out there on the chart. So the 67th percentile means that 67% of the height that I've measured fall below that point, which is at about what, 160, maybe 157, somewhere in there. 67% of the height, if I lined all the kids up, are below that point, and 33% are above. That's a percentile rank. When you look at studies, you will also see some other ways of lining scores up and looking at them in a standard way. You'll see T-scores, stay nines, and Z-scores. And I'm going to focus on Z-scores because that's probably the most common and useful. Z-scores are telling you a child's Z-score. Okay, I've got to get away from just saying child. The Z-score on a measure tells you how much of a standard deviation the score is from the mean. And so it lets you compare two sets of data that are not on the same scale, because a Z-score scale, the mean is always 0 and the standard deviation is always 1. So it can be plus or minus. So let me show you how this works. We're going to look at the Z-scores for someone who took a math test and a reading test. And we calculated that this person's score on the math test, their Z-score, standardized, is 1.5 on math and 0.75 on reading. These two tests were completely different, and a 50% on math did not mean the same thing as a 50% on reading. So I couldn't do it that way. I had to line all the kids' scores up. So for math, that means in the distribution, this score of 1.5 on math is 1.5 standard deviations from the mean. So this score, that's pretty good. That's off into the right tail. We're getting up there. This kid did really pretty well. And if you look at all the percentages under that curve, you could see the percentile ranking there. Now reading, 0.75, look, the child still did okay, but is closer to the mean on the reading. He's 0.75 standard deviations above the mean on a Z-score. Now, I could have given you an example that was negative, where a child was below the mean, because half are above and half are below, that's 0. You're lining all the children up and ranking them. So that's a Z-score.